Hey, welcome back again. Here we go, interpreting graphs of linear equations. Um, for this presentation, what we're going to be talking about is essentially what graphs of linear equations might look like, what our data might look like after we do an experiment for something that might be linear. Also have a little bit of mention of things that are non-linear or things that are not lines. And as we go through the year, we'll see how we deal with things like that. It's really similar. Uh, the first thing that you're also going to notice about this presentation is that it is really, really boring looking. All right. And strangely enough, that when you guys draw graphs and make graphs for this class, you have to be really careful. Everything should look really boring. Nothing should pop out on your page uh, that doesn't belong there. The data should speak for itself. The graph should speak for itself. We don't need anything pretty, like all of our data points don't need to be like little cat faces or, smiley faces or something like that. All that does is distract from what people should really be looking at, and that is the data itself and the relationship for that data. All right, so let's get to some key terms here. First, in any experiment, variables are important. We have two types of variables. We have independent variables. This is something that we are changing or manipulating during an experiment. So this is what we are choosing to change. And when we change this independent variable, it's going to affect what we call the dependent variable, which is the factor that's going to be measured during the experiment. So this is what we're looking at and what will actually change. When we graph these things, we're going to graph our independent variables on the x-axis and our dependent variables on the y-axis. All right, so just to sum it all up, independent variables are the things that we change, and dependent variables are the things that we cause to change. So the independent variable affects the dependent variable. So as we kind of move along here, we also have to take into mind that during any experiment, if we design it correctly, there are going to be things that are called constants, and these are things that don't change during the experiment. See, we can't have too many things changing at once, or else we'll never know what caused our dependent variable to change. So if we are changing too many things, then our experiment is designed poorly, and we're never going to get a real true idea uh, of what variables affect which other variables. All right. So you have to decide these things before you start your experiment, and possibly future experiments mean that you change those constants to see how they might affect something later. All right, but you need to establish a relationship first. So what kind of relationships can we have? If you remember back from your math class, we have things like direct correlations, all right, or direct relationships. These are sometimes called positive correlations or positive relationships as well. And essentially what this means is that if we're looking at our data, so if we look down here, our x-axis, these are our independent variables, that's what we're changing. Our y-axis, this is our dependent variable. What we're noticing is that all of our points, all right, are increasing as we move from left to right. So a direct or a positive correlation means that as we increase the independent variable, our dependent variable increases as well. So direct relationship. Sometimes you can think about these as going the same way. Also, if you look at that line, it has a positive slope, all right, which is where we get the positive correlation name from. We also have indirect correlations, or they might also be called inverse correlations or negative correlations, all right? And as you can see, negative, this goes along with a negative slope that might be on a best fit line. And so this means that as we increase our independent variable, x, our dependent variable gets smaller, okay? And so we see that negative relationship. So there are different types of graphs. We have linear graphs, and when we talk about linear graphs, we're talking about things that look like lines, all right? And we see here that we have a nice, decently straight line through this data. And remember, lines have an equation that goes along with them. It's y equals mx plus b, where m is the slope and b is the y-intercept, all right? And what's special about linear graphs or linear equations is that they increase or they decrease at a regular rate. This means they actually do have a slope. So the slope is what we consider the rate of change. All right, that is the rate that we're talking about. So it either increases with a positive correlation or decreases with a negative correlation. There are other types of graphs. We have exponentials. We have um, logarithmic curves, and there's so many different other shapes, and that sometimes we have to be careful, and we'll need to use some different methods to use them. But for the most part, we can get things into the linear graph like we want, and so we're going to stick with lines for the most part. So also, once we get these equations, we can use them. So we can start plugging in values that maybe we didn't use in our experiment. So if we use a value that's within our range for our dependent variable or independent variable, then we're interpolating data. So this is picking a number that's within the numbers that we were using. And extrapolation means that we're picking values that are maybe way off in the future or way off in the past, so outside of outside of the data. So interpolation is finding values inside the data, so within the range, and extrapolation is finding things outside the range of the data. All right, so that's what the equation is useful for, is that we can then use it to predict future values. All right, so one of the things that I want to point out here is that when we graph these things, we're going to notice that none of our points are ever lined up properly. All right, it's so rare, sorry, it's so rare that we get things that are perfectly lined up in a real world situation. Almost always there's some kind of what we call variability in the data, and variability means that there's slight differences. So it looks like it's following a general pattern. In this case, it looks like it's following a positive correlation, and we're interested in that. That's telling us about the relationship. But notice those points are not lined up perfectly. So what happens when we don't line things up perfectly? We need ways to decide whether or not they line up good enough. All right, so we have two things that we can use for that. One of them is called the correlation coefficient, sometimes known as the R value. All right, this measures basically the strength of the linear relationship. So how linear is the data? All right, if things line up really well, then it has a high correlation coefficient. Then we have the coefficient of determination. This tells us how well that equation fits the data that we have. So this is telling us about the equation. So the first one, correlation coefficient, this is talking about the shape of the graph. Coefficient of determination, our squared value, this is telling us the strength of that relationship as an equation. So how much can we trust the equation? So this one is how much can we trust the data to fit a line. This one is how much can we trust the data to give us a future value or a past value. So good values for these things. And we'll show how we actually graph these in class. 0.95 and above is good for both of them. All right, so we say 0.95 and above for values for R is going to be a strong linear relationship. 0.95 and above for R squared means that we have a strong correlation and we can really trust our values. Now here I have 4 graphs. All right, and these 4 graphs all have the same correlation coefficient of 0.816, which is, if we look, it's kind of in that very weak range. All right, and sometimes this is okay, it's acceptable, and sometimes it's not. And we'll discuss those in different circumstances, and definitely a prob and stats teacher would do a great job of explaining it. But this 0.816, so it's kind of a weak linear correlation. And as we see around in these different graphs, how can they all have the same value? Now, if you look, all of their best fit lines appear to be the same, but that data does not all look the same. So in this first one, all right, this top corner here, we're noticing that all of these data values are kind of spread out, but they're all basically around this line. So they look basically linear. There's a decent linear relationship. Maybe with a correlation value like 0.816, we can't really trust that model very well, but it definitely looks linear, like there's a positive correlation there. And if we jump down here, we see that this data is lined up really, really well almost perfect, and then there's this one stray point. Well, this is what we call an outlier. All right, and so this outlier is actually dragging this line up a little bit, okay, and causing it to tilt up, get a greater positive slope than it should have. All right, and so this value is messing this line up. This would probably be almost a perfect correlation of like 0.1, which is which is 1, or even like a 0.99, but because of this, it drops all the way down to a 0.816. So outliers are bad. If we can, we eliminate them, we get rid of them, and they make our models better. Up here, this is not a line at all. This is a curve. But when we go to fit a line to it, we get this weak linear correlation. It's just basically a guess. But this doesn't belong here at all. This is not a linear correlation. We shouldn't be using a line to match that. And then finally over here, we see all of our data lies on one spot, all right? And so we say the value should be, when it's 8, it could be any one of these things up here for y. But look, there's this stray data point over here, and it gives you a line. So this would not be a linear relationship. This would be like a vertical line, which we know has an infinite slope. But because of this thing, it makes a line out of it, and we think, oh, wow, maybe we can use that for something. All right. And so looking at all these, they might have all the same correlation coefficient, which is weakly linear, but they're not all created equal. So what this really tells us is we need to be smart when we look at our data. We can't just write numbers down. If things are not linear, like this one up here, this curve, we don't use a linear fit. If this one up here, look, this is loosely, but look, this one down here, this has an outlier. So we have ways that we can take care of that. Now, once we get a graph, we want to do an interpretation. And so this is like a paragraph that we would write. And these are all the things that we would write in our paragraph. So what I would do right now is pause the video and go ahead and take these notes, because what we're going to do is we're going to talk about these in just a second. Okay. So when we're talking about relationship, we're talking about direct versus indirect, and we want to mention that in our paragraph. Type of graph, linear, or maybe some type of curve, maybe it's a quadratic or something like that. We want to mention that. We're going to describe what this thing is actually telling us and how it applies to our data. We want to give a description of any types of error, and we want to make sure that we're writing in complete sentences. All right, so I have an example here. This is some data that I came up with for a number of Oreos. If I start stacking Oreos on top of each other, 0 through 8, and I measure all of the heights that go along with them, then I can create this graph that we see over here to the right. So the number of Oreos, 0 through 8, is what we see down here along the bottom. That's our independent variable. All right, and our dependent variable is here on the y-axis. That's the height of the stack. All right. And so as we look at this, we say, all right, what do we do with this? We graph it, we get a best fit line, and this is the equation that we see. All right, so we have a y equals mx plus b, so where our slope is 0.2902, and our y-intercept is 0.01, which is really, really small and really, really close to 0. I also have a correlation coefficient of 0.99, which is outstanding. This means that this data is very linear, and we can definitely trust this equation to start using it for prediction, all right? And so if I'm writing an interpretation for this, what I want to do is I want to start by saying what type of relationship it is. So in the first sentence here, so the data shows that there is a direct linear relationship between the number of Oreos stacked and the height of the stack, all right? So direct linear relationship. Linear because it's in a line, direct because it's a positive slope, all right? And I mention the two variables, the independent and dependent variables in my description. I say, so number of Oreos and the height of the stack, all right? That's the relationship. So the next thing I do is I want to talk about that relationship. And if I have a positive correlation, that means that the number of Oreos, when it's increased, the height of the stack also increases. So that's my description of how those apply to my physical phenomena. All right. There's a strong correlation of 0.99 for this relationship. All right. So we're saying about the strength of that data and the strength of that fit, meaning that the data is very linear. and that this model can be trusted for prediction. That means we can use it to interpolate or extrapolate. All right, so the slope of this graph is 0.2902 Oreos per centimeter. So how do I get Oreos per centimeter? Remember, it's rise over run, okay? So rise over run. So my rise here is going to be the height of the stack. My run here is going to be the number of Oreos. So height in centimeters over Oreos. So this should be, centimeters per Oreo. And so that's going to represent the average height of one Oreo. It's centimeters per one Oreo. So that's how tall each Oreo should be, which is about 0.29 centimeters. So about a third of a centimeter. All right, so that's my next description. So about the physical phenomena. The next thing that I'm going to do is talk about the types of error. And so not every Oreo is perfectly the same height. There is some variability in the height of an Oreo, and this is just because of manufacturing. So not every Oreo is exactly the same. Also, though, there is some experimental error. So just by the fact that a ruler is not a perfect measuring device, we lose some accuracy. So there's some error that comes from that, and this is called experimental error. All right, and so this is an example interpretation. Notice it's really dry and boring, all right, but that's the whole idea. Every interpretation is supposed to be just the facts. What is the data telling us? All right, there you go. That's our video lesson for the day.